Hi everyone, it's our turn today again, and we will talk about another paper about rendering 3D scene from different camera poses, but on input you get only a set of images and you don't have 3D structure, you have to reconstruct it. And the paper's title is NeX, Real-Time View Synthesis with Neural Basis Expansion. So first, let's go and look at the basic concepts. Let's say that we have some scene which we observe. So let's say we have a person here standing and we have some tree on the background. And also we have let's say we have some other object somewhere there, some kind of triangle, I don't know, whatever. So the person is standing the closest to us. Then there's some triangle to the left and a little bit behind, and in the background there is a tree. So what is our input is that we get a series of images. Like, for example, we have a camera here and it provides us a snapshot of this. So we will see a person, then there will be a triangle, and then there will be a tree. And then let's say we have another camera here. And we will get another snapshot of our 3D scene. A person, a triangle, and a tree. A tree somewhere behind the person, so basically you don't really see it because it's occluded. Alright, and we can have like 10, 20, 30 of such snapshots of the scene from different angles. And our aim here is to build some kind of representation of this scene, to be able to rotate the camera in our virtual environment and re-render this scene from different angles at test time. So sort of neural renderer. There are several ways how to do it. Sometimes people use point clouds. Sometimes they represent scenes like meshes. But recently, these approaches are not very popular because there is a little bit better approaches which are more flexible and allow to render with high resolution. So the basic idea here is that we learn a volume so for every let's say we have here X, then we have Y direction here, and we have Z direction there in the depth. So for every coordinate X, Y, Z in this volume, we would like to know what kind of color is it and what is the opacity of this pixel, voxel, or you can think about density, for example, if not opacity, it's roughly the same thing. And then if we know it, if we can reconstruct such a volume, it could be discretized or it could be non-discretized, and I will tell you a little bit later how to be able to learn it without making some assumptions and to making a discrete grid inside this volume. So if for every coordinate we can learn which kind of color is there, then we can just put a new camera somewhere, like, I don't know, at this position, or maybe like from this position, which was not in the training set, and re-render this volume on a novel camera plane. This will allow us to synthesize novel views. So the basic idea, how can we learn such a volume, is the following. So first, we know the positions of the training cameras. So I just redraw this camera 1, camera 2. So I just draw it again here. It's camera 1, then we have camera 2, camera 2. So we initialize our volume somehow randomly. Let's say that we discretize it somehow. We select like a step in every axis, x, y, z, a discrete step, and then we have a volume of size h, w, and d. So heights, widths, and depths. We have heights by widths by depths cells. So what we do now, knowing the camera locations, we can reproject the randomly initialized volume on the camera planes, which are in our training set. So we know what is drawn here because we have pictures. We have picture, and the same thing we know what is drawn for this camera. Triangle and the tree somewhere behind. So our randomly initialized volume is reprojected to both cameras, and then we can compare what we get by reprojecting our volume with original training images and compute the L2 distance between the colors, and that will be our loss. And then we backpropagate to the volume to every location which is visible on the image, to every voxel which is visible here. We backpropagate back and update the values in our volume. How do we project? So let's say we have projection matrix for every camera. Let's say pi. That's not difficult to compute. This is usually done by running a call map. Call map is a library which allows to reconstruct camera locations by feeding there a series of images from different camera poses of the same scene. And this algorithm is called multi-view stereo. It can reconstruct the camera locations based on the descriptors which are calculated at every image. So we calculate descriptors at every, like for example, corners or some key points are detected automatically. And then they can match between the different views. So we would know that like this location of the hand is corresponding to this hand on the other image. And based on this, you can reconstruct the 3D location of the camera plane. And then so basically you have the projection matrices. That's not the scope of this paper. It's like already done, and this library is pretty good, and you can check it on GitHub. I will leave the links in the description. All right, let's define this volume as V, and for every location, let's say this one, we will just say that V, X, Y, Z. And then this VXYZ would be equal to R, G, B, and alpha at this location. All right, let's project this volume using the projection matrix. Then we will get an image. And then at this image, let's look at at any pixel. I will just show you how this pixel color will be calculated. So let's say we shoot a ray from this camera through this voxel. And then obviously we will have a lot of other voxels here intermediately, which we meet along. And the color of this pixel P, which corresponds to this ray, would depend on the values in the voxels which lie on this ray. Let's redraw this ray, and then we will have these voxels on this ray, like 1, 2, 3, 4, 5. 1, 2, 3, 4, and yeah, there is maybe 5 somewhere behind. All right, then the value of this pixel P, so it should be RGB value. So here will be R1, G1, B1, alpha 1, will correspond to the first point. To the second point, we'll have
R2, G2, B2, alpha 2,
and so on. So in this case, we will then have to sum up all the values. So we'll have them n somewhere else. From 1 to n, we will sum up the RGB R1, Gi, Bi, multiplied by the probability that this voxel I, will be visible. And this probability that the voxel I is visible will depend on its order on this ray, because the first one will be visible. That's right here. The first voxel will be visible with probability alpha 1, because if the opacity is high, then it's visible. What about A2? A2 will be visible with probability of alpha 2 multiplied by 1 minus alpha 1. So it means that for the light to travel till this location, it should go through the first node, through the first voxel. And the probability that the light will travel through the first one would be 1 minus alpha 1. And so basically alpha AIs would be equal to a product of alpha i's multiplied by alpha j, where j goes from 1 to I minus 1. So if we define this image as x1, this is a training image, then we get here x1 reconstructed, which we get by reprojection of our volume on the first camera. Then the loss function would be just L2 difference between the x1 minus reconstructed x1. So it's a norm squared. And then we compute this loss and we can backpropagate to the initial voxels here on the array and update their values. So we directly learn the values in the volume. But maybe there is a better way, because here we are bounded by the discretization resolution. We're also bounded by memory, because the higher the resolution, the more voxels we would have in this volume, and the more memory we would require to store the entire scene. So the authors of the paper called NERF came up with another approach, and let's quickly look at the results which they have. They're quite amazing, but this paper which I'm explaining, I will show you results at the end, they're even better. So the idea of NERF is, instead of learning explicitly the values in the volume, we would learn a neural network F, which would take as input x, y, z coordinates, continuous coordinates of the voxel location plus angle v, which is the angle of the ray which falls from the camera, and it will produce us RGB values in this location plus alpha. And then we can do the same thing again, reproject using the camera projection matrix and compute the loss. But in this case, this F is a neural network. And basically this representation of the volume V lies entirely inside the weights of this neural network. And it turned out to be pretty effective, and during inference time we can render with arbitrary resolution, because this F is not discrete and we can sample any XYZ locations and get our desired RGB colors plus alpha. But the problem here is that it's super slow. It takes like 1-2 days maybe to train. 1-2 days, guys, for every scene. You just need to overfit this network for the specific scene for almost 2 days using V100 GPU. And then after that, to render from new angle, you select, like, you can select this novel camera here, and it will take you like 1 hour to render this scene if the scene is like reasonable size. 1 hour to render. So it's quite effective in terms of memory, because you just need to store the weights of this network. But it's super slow to train, and it's super slow to render a novel view. Okay, what can we do instead? And what is the contribution of this paper, which we discuss? Let's look at RGB value. What is RGB value? It's basically a coordinate in the color cube in RGB space. And we can write it like this. RGB is equal, or like, it's a color. It's equal to RGB. RGB, these are 3 coordinates. And then we have a basis. And our basis is 0, 1, 0 is for R. 0, 1, 0 is for B, for G, and 0, 0, 1 for B. This is a basis matrix. Let's call it H. And let's call this coordinates K. So we have one set of coordinates and one basis. And the basis is fixed here. So the first idea which the authors of the paper propose is to increase number of bases here. So basically, instead of learning one set of coordinates RGB, we want to learn more. Or in this case, the color would be K0. So let's say this would be 0 and H0. K0 by H0 plus K1 H1 plus K2 H2 and plus so on. So it does make sense, right? Because H0, H1, H2 in our case, like they're all the same, they all be RGB space. It doesn't make any sense. So that's why there is another proposal from the paper. Let's learn the basis. In this case, they will make basis HI depend on the angle, and it's basically not fixed and randomly initialized at the beginning, or initialized as identity matrix. So initialized as RGB space and then learned using neural network. In this case, the color would be, so they leave the first basis as it is, so it's RGB space. They don't learn it, it's just good to have it. And plus they have a lot of other from 1 to n, ki, hi at v. And so what's happening here is that this is learnable, this is fixed, this is fixed, this is also learnable, and this is learnable. So what's happening? The representation of the scene is the following. So we have one cube for k0. It's a discretized cube, so we have some sort of discretization here. And at every location, at every cell, we would learn three values: r, g, and b coordinates, so which would correspond to the k0 coordinates. And then the basis h0 is fixed, which is just RGB basis. And then we have n more different bases, which we would learn by neural network. So we will use a neural network phi, which would take x, y, z coordinates and would predict. So it's a neural network, I will draw it. And the output would be k1, k2, and so on, kn, where every k is a matrix which defines a basis. And also this network would predict another value, which is alpha. Given a desired location in our 3D space xyz, we would retrieve first the corresponding location in our first tensor, which is learnable. Then we will feed it to the neural network phi, and get coordinates in our k bases, and we will get alpha, which is only a single scalar for every xyz location. But now comes the turn of basis hi. So we will have another network, which we'll define as theta, which will take as input only the angle. It's a three-dimensional angle v, and it's also a neural network, and it will produce for us a set of bases h1, h2, and so on, hn. Now, given all this information, we can easily reconstruct the color for any location. So the function will be still the same. X, the signature x, y, z, v, the same as for NERF. But in this case, this is already not a single neural network, it's a combination of neural networks. And so what we will get here? It's k0, which is just a learnable tensor. H0 is RGB basis. Plus sum of ki, which is produced by f, neural network f. ice component multiplied by h y v, which is basically the same as ice component of the output of network theta. And this will define the first three components. And then we will also get alpha, which is the alpha component, so like the last scalar of the network phi. So that's it. This combination will be converted to RGB values because it will be exactly three coordinates after we sum up everything. And we will get a scalar alpha. After this, we can do exactly the same operation as we did here for projecting and rendering our volume V on novel views and compute exactly the same loss as this one, and compute gradients and update all our networks and the initial volume, which has RGB coordinates here. So that's it. Let's switch to the paper. This is how the scheme looks like in the paper. So this is K0, as I explained already. This is just discretized volume. Then we have this network. I defined it as phi here, which predicts coordinates, and alpha, opacity. And then we sum them up here. And at this step, we use also alpha and this RGB color. So this is color already. After we sum up, we get the color. We use color and alpha and reproject it on novel camera. We get the rendered image and compare this rendered image with the ground truth to compute the loss. That's exactly the same what I have described using my doodles. I hope you liked it. There are like several different quantitative evaluations possible here, different visual quality metrics like PSNR, SSIM, so just defines some sort of similarity between the ground truth and the reprojected views on some holdout test set. And here we can see that NERF, which I have explained, is 1 point below. So it's everywhere below the proposed method, which is much better. But the true strength of this method comes from the fact that we have a decomposed representation of bases and the color coordinates k, which are predicted by two different networks. It means that if we change the angle, it doesn't change the coordinates k. So it means that we can use neural network phi, run it for every xyz coordinate in the discretized volume, and save all the values, including k0. So k0 we don't need to save because it's already saved. It's out of the network. It's just updated explicitly using gradient descent. And then using network, we save all k1, kn for every location in our grid, in our volume. And we forget about network phi. And every next time we want to re-render the scene from the novel camera pose, we just retrieve these pre-computed values. And the only thing which we need to do is to do a forward pass of this network theta given the angle v which defines the camera pose. So it's super fast. This is like 5-6 layers, multi-layer perceptron, and the input is a single vector v which defines the angle. It's super fast, and the authors claim that their method can achieve 60 frames per second online rendering at resolution of around 1000 pixels by 700, which is significant speed up compared to NERF. For comparison, to render the same scene, it will take NERF 55 seconds. So it's like more than 100x improvement in speed of rendering. Of course, it takes some time to pre-render it, but we can neglect it. As long as we pre-rendered and saved all the coordinates k, we can do really fast inference, which is amazing. And this is what you can see on this demonstration. And also they have online demos where you can just in your browser rotate the scene and see how this online rendering is working. This is pretty amazing. So I think this is a big step forward in the neural rendering and in representation of 3D scenes based learning 3D scenes based on multiple input images. And I think this overall is a really great paper. Check the links in the description. I will leave some links to the source code, to the NERF paper, to some other related papers. If you're interested, you can read more. I'm really glad that you made it to this point. So thank you for listening again. Subscribe if you're not subscribed, push the like button, and see you next time.